Hello, this is David. Welcome to Part 2, Topic 5, John Hull, Chapter 19 on Volatility Smiles. This is a brief chapter, although the concept is relatively difficult if you're brand new to it. And so we start with the aim, define volatility smile. And so the stylized version here, that is to say without specific numbers, we don't need to be concerned with the numbers actually, specifically in the case of the volatility smile, at least on the level of the FRM exam. We have here a classic volatility smile, and you can see here this blue line resembles somewhat a smile. This could sometimes be called also a volatility smirk, but the volatility smile is going to be defined as a plot on the y-axis of volatility, recall that's annualized standard deviation, against the strike price most commonly. And so this is the basic variation that John Hull introduces. We're going to see there's a couple other choices we can make with respect to the x-axis. However, our y-axis is going to generally be annualized standard deviation. And so it's going to be a plot of specifically implied volatility against the strike price. Now, also we have something called the volatility term structure where we have the same implied volatility, but the plot in this case of the x-axis is going to be over time or time to maturity or maturity, and then we'll see that in that case it's a different x-axis. But the key thing here about this volatility smile is it's based not on historical volatilities but implied volatilities. And so we see here a volatility skew, which in this case uses some actual numbers from Google stock options. So this is I ran this quite a while ago, a couple of years ago maybe, or longer. And we have here a typical smile-like characteristics, or in the case of what John Hull calls the skew, as the strike price increases, the volatility decreases. So here's the skew portion in particular. And so that's an increasing stock price as the x-axis goes to the right. And what does that mean in terms of options? So I notice I would draw attention to the fact that here at lower strike prices, that implies in the money calls. So as we move to the left, increasingly deeply in the money calls, but also with lower strike price, it's out of the money puts. And so over here on the right, as the skew sort of gives rise to some, gives over to some increasing implied volatility as the strike price increases, we have over here, as we move to the right, higher strike price, we have both out of the money calls and in the money puts. So John Hull employs put-call parity, once again, one of the most useful tools in option pricing and option mechanics, and he applies it in this way. First, we've got put-call parity, and then what initially looks like the same put-call parity duplicated again. But the key difference here is this put-call parity is based on model prices, or the Black-Scholes output. This line here is based on market prices. And so that he then does a subtraction to show this formula and the conclusion that the dollar pricing error when the Black-Scholes model is used to price a European put option should be exactly the same as the dollar pricing error when it is used to price a European call option with the same strike price and time to maturity. You'll recall this condition here, identical strike and time to maturity, is a condition of the put-call parity. And so this is the proof, so to speak, of showing that the dollar pricing error when the model is used is going to be the same for the call as for the put. Okay, so now we get really to the essence of the entire chapter really, and by the way, the most testable portion. And that is to say that one way to interpret the smile is that it implies a distribution. And so the way I would set this up is that if we think about that Black-Scholes option pricing model, you will recall that a key assumption there is the log normal property of prices. The returns are normal. The continuous log returns are normal, means the prices are log normal. And so that if we just stylistically again characterize the log normal distribution, we could ask the following question: if the Black-Scholes option pricing model were accurate, completely accurate, what would be the implied volatility smile? Well, in fact, it would be a horizontal line like this. Why? Because that Black-Scholes model is not only assuming constant volatility, but a log normal distribution, which is to say that as the strike price varies, notice this, we don't really assume any change in the volatility, or put in terms of the volatility smile, just because the option moves from let's say an out of the money put to an in the money put, we're not changing the volatility assumption. So in this way, that a stock that behaved according to log normal property would be consistent with an implied volatility smile that is in fact flat. Okay, so we use that to then understand the point that John Holl's making. And he's making this, that if we go out into the market and infer the implied volatility smile, and I remind you again, this y-axis is implied volatility. What is that? That is the volatility that would be input into the model consistent with an observed price. So it's based on observing different market prices and solving for the implied volatility. So he's then saying, well, what do we do with the fact that we observe not a straight line, which would be consistent with a log normal distribution, but in fact a smile? And so one way to cope with that, or to interpret that, is to say, well, what the market's saying is that the distribution of the stock is in fact not log normal, right? It's different than the log normal. And specifically in the case of a smile, because we've got higher implied volatility on the left and higher implied volatility on the right, that would correspond to a distribution that has heavier left and right tails. Do you see how on the left here, so this would be a deeply out of the money put or a deeply in the money call? We have a higher implied volatility than we would have at the money. Higher implied volatility would correspond with a heavier left tail, hard to see here, but see this dark blue is peaked, that's kurtosis, peakedness, corresponding to heavy left tail. And over on the right also, higher implied volatility, higher implied volatility also corresponding to heavier right tail. Okay, so that's the key. The key again is the interpretation that in observing an implied volatility smile, we assume that the market is telling us that the distribution is not log normal. And so we have different ways of looking at that. Here is an implied smile, but notice this is a sort of an inverted, we could call this a frown. What would that be? How would we characterize, how would we interpret that? Well, we'd say that's implying for the distribution of the stock or asset, light left tail, light right tail. Okay, similarly over here, and this is the kind of question that the exam, so this is why I say the chapter is really all about this. What if we see here this implied volatility sort of inverse unexpected smirk? Well, it would correspond to a light left tail, but a heavy right tail. Okay, let's do two more that are more typical. Those first two, we want to look at a little more, I made those up. These are more typical. Here's what we expect, and that by that I simply mean it tends to be observed in the equity markets. An implied volatility skew. What is that telling us? It's telling us, it's implying a heavy left tail, but a light right tail. Okay, when there's also another interpretation here of the smile could be jumps in the underline. We're asked, explain why foreign exchange rates are not necessarily log normally distributed and the implications this can have on option pricing and implied volatility. So there were two conditions for a log normal asset price distribution: constant asset volatility and a smooth, aka diffusion process. Neither of these is satisfied for an exchange rate. The volatility of the exchange rate is not constant, and exchange rates exhibit frequent jumps. Now we're asked about the volatility smile for equity options and give possible explanations for its shape. So the two that John Hall constantly has put forth is this first, capital structure leverage. The idea that capital structure may explain why there's a volatility smile. Higher leverage may give rise to higher volatility. I actually think this one is difficult and many nuances, subject to much debate on the forum, and ultimately even a little bit debatable. However, I think the more important one for our purposes is crashophobia. And that's the idea that market participants fear a market crash and they price the options accordingly. So notice here, this suggests that deeply out of the money puts are priced with a high implied volatility. So keep that thought in mind. I'm going to go back. No, I'll go forward here. Keep that thought in mind. So crashophobia, would be concerned with here. Notice this is strike price. So as you move over here to the left, deeply out of the money puts would be more expensive and corresponding to higher implied volatilities. Why might they be more expensive? Because market participants demand them more. They're buying them for what we would call tail insurance. That's the crashophobia. I think that's a very plausible explanation. Alternative ways of characterizing the volatility smile. So notice we said the primary way to view the x-axis is the strike price, but we can also use the ratio of strike to forward price, or also very useful is just the option delta, right? So where the at the money call delta might be 50, so we would have what we call 50 delta options. So we could have we could just use the delta here as the x-axis. I said before that instead of on the x-axis having strike price or a ratio or even delta, we could have just time to maturity. And so that's a volatility term structure, a plot of volatility and the maturity. And it tends to be an increasing function for the call option, but it really could vary because, again, this implied volatility is a function of the market prices, which are going to be informed by several factors, including technical factors just like liquidity and supply and demand. Now we can combine this term structure with the volatility smile and we get a volatility surface. The volatility smile does complicate the calculation of the Greeks. So we have a sticky strike rule, that the implied volatility of an option remains constant from one day to the next, and a sticky delta rule. The relationship between an option price and the ratio of its stock to strike price is relatively constant. Now, finally, the impact of asset price jumps on volatility smiles. Where there's a large jump, either up and down as anticipated, the actual distribution is not log normal, but rather bimodal, two humps. An at the money option has a higher volatility than both an out of the money option and an in the money option. So if the asset price are not really diffuse, but rather have the jumps, this implies an upside down volatility smile or a volatility frown that peaks in the middle, or could imply. And that concludes the brief chapter on volatility smiles. Thank you.